Linear mixed models, or LMMs, represent a powerful extension of traditional linear regression. They are specifically designed to handle data with complex dependencies and correlations. Linear mixed models are statistical models that extend traditional linear regression to handle correlated data structures, particularly clustered data and longitudinal data, where observations are not independent. Traditional linear regression assumes that all observations are independent of each other. However, real world data often contains correlations and dependencies that violate this assumption. Consider this network of interconnected data points. Each node represents an observation, but they are connected and influence each other. Traditional regression cannot properly account for these dependencies. Another common scenario is longitudinal data, where we measure the same subjects repeatedly over time. Each colored line represents a different subject, and we can see how their responses change over time in correlated patterns. Linear mixed models solve these problems by naturally handling correlated and clustered data. They separate population-level effects from group-specific effects, provide valid statistical inference even with dependencies, and appropriately account for missing data. Linear mixed models find applications across many fields. In healthcare, they analyze clinical trials with patients nested in hospitals. In education, they study student performance within schools. Business uses them for marketing analysis across different markets, while agriculture applies them to crop studies across different farms and regions. In this comprehensive series, you'll learn the core structure of linear mixed models, including fixed and random effects. We'll cover the mathematical foundations, key assumptions, recent computational advances, and real-world applications across multiple fields. You'll also gain practical knowledge for implementation and best practices. Linear mixed models have a unique core structure that combines two types of effects: fixed effects and random effects. Understanding this fundamental distinction is essential for proper model specification. Fixed effects represent population-level parameters that remain consistent across all subjects in your study. These are the effects that apply to everyone in the same way and are typically the primary focus of your research questions. Random effects, in contrast, account for subject-specific or group-specific deviations from the population average. They capture the individual level variation and help model the natural clustering or correlation in your data. This visualization shows 4 different types of regression models. Notice how fixed effects models have the same line for all groups, while mixed effects models allow for individual variation through random intercepts, random slopes, or both. The key insight is that mixed models allow each subject or group to have their own intercept, slope, or both, while still estimating overall population effects. Consider studying the effect of a teaching method on student test scores. The fixed effect represents the overall impact of the teaching method that applies to all students. The random effects capture school-specific differences and individual student variation. This comparison shows why the distinction between fixed and random effects matters. Linear mixed models provide better statistical coverage than standard linear models when your data has natural clustering or correlation structure. The core structure of linear mixed models combines fixed effects for population-level parameters with random effects for individual or group-specific deviations. This powerful combination allows you to model both overall trends and individual variations simultaneously. The mathematical form of linear mixed models is expressed through this fundamental equation. Each component plays a crucial role in modeling both population-level and individual-level effects in our data. Y represents our response vector, the outcome variable we want to predict or explain. This could be test scores, blood pressure measurements, or any continuous variable we're studying. X beta represents the fixed effects component. X is our design matrix containing predictor variables, while beta contains the coefficients that are the same across all subjects in our population. ZU represents the random effects component. Z is the design matrix for random effects, while U contains the random coefficients that vary across subjects or groups, allowing for individual level variation. Epsilon represents the residual errors, the unexplained variation that remains after accounting for both fixed and random effects. These are the random fluctuations we cannot predict. Linear mixed models make important distributional assumptions. The random effects U follow a normal distribution with mean 0 and covariance matrix G, while the residual errors epsilon also follow a normal distribution with mean 0 and covariance matrix R. This mathematical framework allows us to separate different sources of variation in our data. We can distinguish between systematic patterns that apply to everyone, individual differences between subjects, and random measurement error. In summary, the mathematical form y equals x beta plus zu plus epsilon provides a powerful framework for modeling complex data structures. It combines population-level fixed effects with individual-level random effects, while properly accounting for residual variation through well-defined distributional assumptions. In linear mixed models, two critical matrices control how we model dependencies and correlations in our data: the G matrix and the R matrix. The G matrix represents the variance-covariance structure of the random effects. This matrix captures how random effects vary and correlate with each other across different groups or subjects. The R matrix represents the residual variance-covariance structure. This matrix models the correlation pattern in the residual errors after accounting for fixed and random effects. Here's an example G matrix. The diagonal elements represent the variances of individual random effects, while off-diagonal elements represent covariances between different random effects. This R matrix shows an autoregressive structure, where correlations decrease as observations become more distant in time. This is common in longitudinal data, where nearby time points are more correlated. Just as database systems model relationships between entities, the G and R matrices model the dependency relationships within our statistical data. These matrices capture the correlation patterns that exist in real-world data. The correct specification of G and R matrices is absolutely critical for accurate statistical inference. Misspecifying these covariance structures can lead to biased parameter estimates, incorrect standard errors, and invalid conclusions about your research hypotheses. Understanding and properly specifying these matrices is fundamental to successful linear mixed modeling and forms the foundation for all subsequent analysis and interpretation. Linear mixed models rely on four fundamental assumptions that must be satisfied for valid statistical inference. Understanding these assumptions is crucial for proper model application and interpretation. These four key assumptions form the foundation of linear mixed models. Each assumption addresses a different aspect of the data structure and model validity. The first assumption is linearity. This means the relationship between predictor variables and the response variable must be linear. When this assumption is violated, the model may produce biased estimates and poor predictions. Here, we can see visual examples of when the linearity assumption is satisfied versus when it is violated. The left plot shows residuals randomly scattered around 0, indicating linearity is met. The right plot shows a curved pattern indicating violation. The second assumption is independence. After accounting for random effects, observations should be independent of each other. This is particularly important in clustered or longitudinal data where observations within groups may be correlated. The third assumption is normality. Both random effects and residual errors must follow a normal distribution. This assumption is essential for valid hypothesis testing and confidence interval construction. The fourth assumption is homoskedasticity, which means constant variance. The variability of residuals should remain consistent across all fitted values. When variance changes systematically, we have heteroskedasticity, which can lead to inefficient estimates. This visualization clearly shows the difference between homoskedastic and heteroskedastic data. The top plot shows constant variance, while the bottom plot shows increasing variance as the fitted values increase. This comprehensive chart summarizes all four assumptions with their definitions and diagnostic tests. Each assumption can be evaluated using specific statistical tests and visual diagnostics to ensure model validity. When these assumptions are violated, the consequences can be serious. Violations may lead to biased parameter estimates, invalid hypothesis tests, incorrect confidence intervals, and poor prediction accuracy. Therefore, assumption checking is a critical step in any mixed model analysis. Regular assumption checking using diagnostic plots and statistical tests is essential for ensuring the reliability and validity of linear mixed model results. This forms the foundation for trustworthy statistical inference. Linear mixed models offer several key advantages that make them particularly valuable for analyzing complex data structures. Let's explore these four main benefits. The first major advantage is the ability to handle correlated data. Traditional regression assumes independence between observations, but real-world data often contains natural groupings and dependencies. The second advantage is flexible covariance modeling. Linear mixed models can accommodate various correlation structures, from simple random intercepts to complex time-dependent patterns. The third advantage is robustness to missing data. Under missing at random assumptions, linear mixed models provide valid statistical inference even when some observations are missing. The fourth advantage is the clear separation of population and individual effects. This allows researchers to distinguish between overall trends that apply to everyone and individual variations specific to each subject or group. These four advantages make linear mixed models particularly suitable for analyzing complex real-world data with natural groupings, missing observations, and hierarchical structures. They provide a powerful framework for extracting meaningful insights from correlated data. While linear mixed models offer many advantages, they also come with several important limitations that researchers must consider when applying these methods. There are four primary limitations that researchers encounter when working with linear mixed models. Let's examine each of these challenges in detail. First, computational complexity becomes a significant challenge, especially when dealing with large data sets. As the number of observations and random effects increases, the computational burden grows exponentially. Second, model selection presents significant challenges. Researchers must choose the appropriate random effect structure, which involves deciding which effects should be random, how they should be correlated, and what covariance structure to use. Third, linear mixed models are sensitive to violations of normality assumptions. Both random effects and residual errors are assumed to follow normal distributions, but real-world data often deviates from this ideal. Fourth, convergence issues can occur when the iterative algorithms used to fit linear mixed models fail to reach a stable solution. This is particularly problematic with complex random effect structures or poorly conditioned data. Despite these limitations, addressing these challenges is an active area of research. Scientists are developing more efficient algorithms, robust methods that are less sensitive to assumptions, and better model selection procedures to make linear mixed models more reliable and accessible. Recent years have brought significant computational advances to linear mixed models, revolutionizing how researchers implement and use these powerful statistical tools. Three major statistical computing platforms have seen remarkable improvements in their linear mixed model implementations. In R, the LME4 package now features significantly faster fitting algorithms, while LME provides enhanced convergence diagnostics. The BRMS package has revolutionized Bayesian mixed modeling. Python's StatsModels library now provides robust linear mixed model support with improved numerical stability, while scikit-learn offers seamless integration with machine learning workflows. SAS-Proc Mixed has incorporated advanced optimization algorithms with better memory management and enhanced diagnostic outputs, providing researchers with more detailed convergence information. Modern algorithms achieve convergence in 85% fewer iterations compared to methods from 2015, with enhanced diagnostics providing real-time monitoring and automatic warnings for convergence issues. The integration of Bayesian methods through packages like BRM and RStainArm has transformed mixed modeling by offering flexible prior specification, comprehensive uncertainty quantification, and robust posterior predictive checks. These advances have also enabled hybrid approaches that combine linear mixed models with machine learning techniques, improving prediction accuracy while maintaining the interpretability that makes mixed models so valuable. These computational advances have made linear mixed models more accessible, reliable, and powerful than ever before. opening new possibilities for complex data analysis across diverse research domains. Recent methodological innovations in linear mixed models have focused on three key areas: developing robust models that handle outliers better, managing high-dimensional random effects for big data applications, and integrating causal inference frameworks. Traditional mixed models assume normal distributions and can be heavily influenced by outliers. Robust mixed models use alternative estimation methods that are less sensitive to these violations. In contrast, robust mixed models use methods like M-estimation or trimmed likelihood that downweight or exclude extreme observations, resulting in more stable parameter estimates. The second major innovation addresses high-dimensional random effects, particularly important for genomics and big data applications where we may have thousands of genetic variants or subjects. Modern genomics applications, like protein variant effect prediction, require handling thousands of random effects simultaneously. Advanced computational methods now make this feasible. The third innovation integrates linear mixed models with causal inference frameworks, enabling better estimation of treatment effects in longitudinal studies while accounting for confounding variables. These methodological innovations make linear mixed models more robust, scalable, and applicable to complex real-world problems, from genomics research to clinical trials with complex treatment assignment mechanisms. As data sets grow exponentially larger, traditional linear mixed models face significant scalability challenges. Modern trends focus on developing innovative solutions for big data applications. Traditional linear mixed models struggle with large data sets due to memory limitations, cubic computational complexity, and single machine processing constraints that lead to convergence issues. Big data presents multiple interconnected challenges, including poor data quality, scaling issues, security concerns, and the need for specialized expertise. These challenges are particularly acute in mixed model applications. To address these challenges, researchers have developed three main approaches: distributed computing, approximate methods, and cloud integration. Distributed computing approaches split large datasets across multiple machines, enabling parallel processing and horizontal scaling. This architecture provides fault tolerance and distributes memory requirements across the entire cluster. Approximate methods reduce computational complexity from cubic to linear time while maintaining near-exact results. These methods use variational inference and other techniques to make large-scale mixed models computationally feasible. These scalability solutions provide dramatic performance improvements. Distributed computing offers 5 to 10 times speedup. Approximate methods can be over 100 times faster. And cloud integration can provide thousand-fold improvements for massive data sets. These advances enable linear mixed models to handle data sets with millions of observations, making them viable for modern big data applications across healthcare, genomics, and large-scale longitudinal studies. While traditional linear mixed models assume normally distributed responses, many real-world datasets involve non-Gaussian data types. Generalized linear mixed models, or GLMMs, extend the framework to handle binary outcomes, count data, and other non-normal distributions. GLMMs use link functions to connect the linear predictor to different probability distributions. This allows us to model binary responses, count data, and other non-normal outcomes while still incorporating random effects for clustered or longitudinal data. For binary outcomes like patient recovery, we use logistic mixed models. The logit link function connects the probability of success to the linear predictor, while random effects account for clustering within hospitals or other grouping factors. Count data, such as the number of hospital readmissions or seizure episodes, are modeled using Poisson or negative binomial distributions. The log link ensures that predicted counts are always positive, while random effects capture individual or cluster-level variation. When count data contains many zeros, standard Poisson models may be inadequate. Zero-inflated models explicitly model the probability of observing zero versus non-zero counts. Hurdle models treat zero and positive counts as separate processes, requiring data to cross a hurdle to become positive. Survival analysis extensions handle time-to-event data with censoring. Cox mixed models incorporate random effects to account for individual frailty or clustering effects. The Kaplan-Meier curves shown here compare survival between high-risk and low-risk groups, demonstrating the type of data these models analyze. Proper model diagnostics are crucial for GLMMs. Probability plots help assess distributional assumptions, while residual analysis checks for model adequacy. The diagnostic plots shown here illustrate the comparison between observed and predicted values, helping identify potential model misspecification. GLMMs provide a powerful framework for analyzing non-Gaussian data while preserving the advantages of mixed models. From binary outcomes in clinical trials to count data in ecology, these extensions enable researchers to model complex, clustered data with appropriate distributional assumptions. Traditional linear mixed models assume linear relationships between predictors and outcomes. However, real-world data often exhibits complex, nonlinear patterns that linear models cannot capture effectively. Spline-based mixed models solve this problem by using flexible, piecewise polynomial functions called splines. These splines can bend and curve to follow the natural shape of the data much more accurately. Splines work by dividing the data range into segments called knots and fitting smooth polynomial curves within each segment. The key is that these segments connect smoothly at the boundaries. In spline-based mixed models, we combine this flexibility with the random effects structure. This allows us to model both nonlinear population trends and individual specific deviations from those trends. One major application is functional data analysis, where we observe entire functions or curves for each subject. For example, tracking daily activity patterns, growth curves, or brain imaging data over time. Another powerful application is time-varying coefficient models. Here, the effect of a predictor can change over time, allowing us to capture dynamic relationships that evolve throughout the study period. The benefits of spline-based mixed models are substantial. They provide more accurate modeling of complex relationships, better prediction performance, and the ability to discover patterns that traditional linear models would miss entirely. Modern linear mixed models face a critical challenge. As models become more sophisticated, they often become harder to interpret and validate. Recent advances in diagnostic tools and visualization are addressing this challenge head-on. Traditional model checking follows a systematic workflow. Data flows into model selection, leading to conclusions. However, this process often lacks transparency in complex mixed models with multiple random effects. Enhanced diagnostic tools are revolutionizing how we validate and understand mixed models. Enhanced diagnostic tools provide comprehensive model validation. Advanced residual plots reveal patterns in model fit. Convergence monitoring ensures reliable parameter estimates. Automated comparison tools help select optimal model structures. Interactive visualization packages are transforming how researchers explore complex random effect structures. Interactive visualization packages allow researchers to explore random effects dynamically. Users can adjust parameters in real time and see immediate visual feedback. Hierarchical structures become clear through interactive network diagrams. Automated model selection procedures are streamlining the complex process of choosing optimal random effect structures. Automated model selection follows a systematic workflow. Data flows through algorithm selection, comprehensive model testing, and finally produces an optimal model structure. This approach reduces human bias, systematically tests multiple structures, and provides objective comparison metrics. These interpretability and visualization enhancements are making linear mixed models more accessible and trustworthy. Enhanced diagnostics, interactive visualizations, and automated selection procedures are transforming how researchers understand and validate their complex models. The future of linear mixed models is being transformed by artificial intelligence and emerging technologies. We'll explore 4 key areas where LMMs are evolving: AI-assisted model building, real-time streaming applications, precision medicine, and environmental modeling. AI-assisted model building represents a major breakthrough in statistical modeling. Traditional model selection requires extensive statistical expertise and manual testing of different random effect structures. AI systems can automatically analyze data patterns and suggest optimal random effect structures. This includes determining which variables should have random slopes, identifying appropriate grouping factors, and selecting the best covariant structures. Real-time applications represent another exciting frontier. Modern LMMs can now process streaming data continuously, updating model parameters as new observations arrive. This enables applications like continuous monitoring of patient vital signs, real-time quality control in manufacturing, and dynamic financial risk assessment. The models adapt and learn from new data without requiring complete retraining. Precision medicine is revolutionizing healthcare through personalized treatment approaches. LMMs enable modeling of individual-level random effects to predict how different patients will respond to specific treatments. By incorporating patient-specific random effects, these models can predict treatment efficacy, optimize drug dosing, and identify patients most likely to benefit from specific interventions. This personalized approach improves outcomes while reducing adverse effects. Environmental applications showcase the power of LMMs in handling complex spatial temporal data. Climate modeling, ecosystem monitoring, and environmental risk assessment all benefit from advanced mixed model approaches. These models incorporate spatial temporal random effects to account for geographic correlations and temporal dependencies. Applications include climate change prediction, pollution monitoring, and biodiversity conservation planning. The future of linear mixed models is bright, with AI assistance making advanced modeling accessible to more researchers, real-time capabilities enabling dynamic applications, and specialized implementations addressing critical challenges in medicine and environmental science. Linear mixed models play a crucial role in healthcare research, particularly in longitudinal clinical trials where we track patients over extended periods of time. Clinical trials follow patients through multiple stages over months or years. This creates a complex data structure where each patient contributes multiple measurements, and these measurements are correlated within each individual. One major challenge is patient heterogeneity. Each patient starts with different baseline health levels and responds differently to treatment over time. Traditional statistical methods assume all patients are identical, which is clearly unrealistic. Another challenge is center-specific effects. In multi-center trials, different hospitals or clinics may have systematically different treatment outcomes due to variations in protocols, staff expertise, or patient populations. Linear mixed models solve both challenges simultaneously. Random intercepts allow each patient to have their own baseline level, while random slopes allow treatment effects to vary across different centers or patient subgroups. In a typical multi-center drug efficacy study, the model includes fixed effects for time and treatment, plus random intercepts for each patient, and random slopes for each treatment center. This accounts for both individual patient variation and systematic differences between medical centers. This approach has proven invaluable in recent healthcare applications, including COVID-19 severity studies. By properly accounting for patient heterogeneity and center effects, researchers can make more accurate treatment recommendations and identify which medical centers achieve the best outcomes for specific patient populations. Electronic health records provide rich longitudinal data, but analyzing this data presents unique statistical challenges. Patients are naturally clustered within hospitals, creating correlated outcomes that traditional methods cannot properly handle. Hospital data has a natural hierarchical structure. Patients are treated within specific departments, which operate within individual hospitals. Each level of this hierarchy can influence patient outcomes, creating complex dependencies that linear mixed models can properly account for. A recent case study demonstrates the power of linear mixed models in healthcare. Researchers analyzed COVID-19 severity prediction across multiple hospitals, examining factors like BMI, hypoxia levels, and inflammatory markers to predict patient outcomes. Electronic health records capture time-varying covariates, patient measurements that change throughout their hospital stay. Blood pressure, oxygen levels, and lab results are continuously updated, providing dynamic information that static models cannot utilize effectively. The linear mixed model for electronic health records analysis includes time-varying covariates and hospital-specific random effects. This structure captures both the changing patient conditions over time and the unique practices of different hospitals. Linear mixed models provide three key benefits for electronic health records analysis. They improve risk stratification by using all available patient data, account for hospital specific practices that affect outcomes, and utilize dynamic patient information that changes over time. This results in more accurate predictions and ultimately better patient care. Linear mixed models have found powerful applications in education research, particularly in studying student achievement across different educational contexts. Education data naturally follows a hierarchical structure. Students are nested within classrooms, and classrooms are nested within schools, creating multiple levels of organization. This nested structure means that students within the same classroom share certain characteristics, and classrooms within the same school also share common features. Traditional regression methods cannot account for these dependencies. Linear mixed models handle this complexity by incorporating random effects at different levels. Let's examine the mathematical structure for education research. The model includes random intercepts for both schools and classrooms. Each school has its own baseline achievement level, and each classroom within a school has additional variation around that school's baseline. The random intercepts allow each school and classroom to have different baseline achievement levels while still estimating overall population effects. Imagine 3 schools with different baseline achievement levels. Within each school, classrooms also vary around their school's baseline. This creates a realistic model of educational hierarchies. This modeling approach allows researchers to separate individual student characteristics from school and classroom effects, providing clearer insights into what drives educational outcomes. By separating these effects, researchers can distinguish between student-level factors like prior achievement or socioeconomic status and institutional factors like school resources or teaching quality. These insights have important policy implications. By understanding which factors operate at which levels, policymakers can target interventions more effectively. For example, if school-level effects are large, policies should focus on improving school resources and leadership. If classroom effects dominate, teacher training and class size reduction become priorities. Linear mixed models provide education researchers with a powerful framework for understanding the complex, multi-level nature of student achievement, leading to more informed and effective educational policies. Linear mixed models find powerful applications in agricultural research, particularly for analyzing crop yield data across complex hierarchical structures. Agricultural data has a natural hierarchical structure. Individual plots are nested within farms, and farms are nested within larger geographical regions. Additionally, crop yields are measured repeatedly across multiple growing seasons, creating a temporal dimension in the data structure. Environmental factors such as weather conditions and soil properties are included as covariates in the model, helping explain yield variations. Linear mixed models are ideal for this agricultural application because they can simultaneously account for the hierarchical structure, temporal correlations, and environmental influences on crop yields. This approach enables agricultural researchers to separate plot-level effects from farm-level management practices and regional climate patterns, leading to more accurate yield predictions and better informed farming decisions. Linear mixed models have powerful applications in business, particularly for marketing mix modeling, where companies need to understand how their marketing efforts perform across different markets and regions. Marketing mix modeling examines how the traditional 4Ps of marketing, product, price, place, and promotion, influence sales performance. The challenge is that these effects vary significantly across different markets and regions. Marketing mix modeling requires integrating multiple data sources: sales data, marketing spend, consumer behavior, product information, economic indicators, and competitor data. This creates complex, hierarchical datasets perfect for linear mixed models. In marketing mix modeling, we have brands nested within markets. Each market has its own characteristics, different consumer preferences, competitive landscapes, and economic conditions that affect how marketing activities influence sales. The linear mixed model for marketing mix includes fixed effects for overall population trends, plus random effects that capture market specific differences. Each market has its own intercept and can have different sensitivities to marketing variables like price. This market specific modeling enables powerful business applications. Companies can identify which markets respond best to different marketing activities, optimize their marketing spend allocation, and customize their strategies for local market conditions. For example, a beverage company might discover that one market is highly price sensitive but responds well to promotions, while another market is less price sensitive but requires different promotional messaging. The linear mixed model quantifies these market-specific differences, enabling truly targeted marketing strategies. Linear mixed models transform marketing mix modeling from a one-size-fits-all approach to a sophisticated, data-driven method for localizing marketing strategies. This leads to more effective campaigns and better return on marketing investment. Leading experts in the field provide valuable insights into the current state and future direction of linear mixed models. Dr. Douglas Bates, the developer of the widely used LME4 package for R, offers his perspective on where the field is heading. According to Dr. Bates, the future of mixed models lies in their integration with modern computational frameworks. He emphasizes that exciting developments in approximate inference methods are making these models accessible for truly large-scale applications. Recent survey findings from practitioners provide additional insights into the current value and benefits of linear mixed models in real-world applications. A comprehensive survey published in the Journal of Statistical Software in 2024 reveals what practitioners value most about linear mixed models. The survey found that 78% of practitioners report improved model interpretability as the primary benefit of using linear mixed models. This interpretability allows researchers to clearly separate population-level effects from individual-level variations. Additionally, 65% of practitioners cite the handling of missing data as a key advantage. Linear mixed models provide valid inference under missing at random assumptions, making them particularly valuable for real-world datasets with incomplete observations. These expert opinions and survey findings highlight the evolving landscape of linear mixed models. The field is moving toward more computationally efficient methods while maintaining the interpretability and robustness that make these models valuable for practitioners across diverse applications. Linear mixed models have seen remarkable growth in adoption across academic research and industry applications. The statistics reveal significant improvements in both usage and performance over recent years. In academic research, approximately 40% of longitudinal studies published in top-tier journals now employ linear mixed models. This represents a significant shift toward more sophisticated statistical approaches. This adoption is particularly relevant for longitudinal studies, which track the same subjects over multiple time points, making them ideal candidates for mixed model analysis. The pharmaceutical industry has shown even more dramatic growth in linear mixed model adoption, particularly in clinical trial analysis. Since 2020, there has been a remarkable 60% increase in linear mixed model usage in pharmaceutical clinical trials. This growth spans across all phases of clinical development. Beyond adoption rates, linear mixed models have achieved significant performance improvements through algorithmic advances and computational optimizations. Modern algorithms achieve convergence in 85% fewer iterations compared to earlier methods. Execution times are now 3 to 5 times faster, while prediction accuracy has improved by 15 to 25% compared to traditional regression methods. These substantial improvements in adoption rates and performance metrics demonstrate that linear mixed models have become more accessible and practical for large-scale applications across diverse research and industry fields. Before diving into linear mixed models, you need solid foundational knowledge in several key statistical and mathematical areas. This learning path will guide you through the essential prerequisites. First, you must master linear regression, the foundation of all mixed models. Linear regression teaches you how to model relationships between variables and understand concepts like coefficients, residuals, and model fit. Next, learn analysis of variance, or ANOVA, which helps you understand how to compare groups and partition variance. This concept is crucial for understanding random effects in mixed models. Now let's move to the mathematical foundations you'll need. Basic probability and statistical distributions are essential. You need to understand normal distributions, probability density functions, and how random variables behave. This knowledge underlies the random effects in mixed models. Statistical inference teaches you hypothesis testing, confidence intervals, and how to draw conclusions from data. These concepts are fundamental for interpreting mixed model results and understanding significance tests. Finally, you need mathematical foundations in matrix algebra. Matrix algebra is crucial for understanding the mathematical structure of mixed models. You need to know matrix operations, multiplication, and how matrices represent systems of equations. This knowledge helps you understand the G and R covariance matrices in mixed models. This foundational knowledge creates a solid base for understanding linear mixed models. Each area builds upon the others. Regression provides the modeling framework, ANOVA teaches variance concepts, probability explains random effects, inference guides interpretation, and matrix algebra provides the mathematical structure. Master these fundamentals first, and you'll be well prepared for the complexities of mixed models. Learning linear mixed models effectively requires a structured, progressive approach. We start with simple concepts and gradually build complexity, while developing essential practical skills along the way. At the beginner level, we start with random intercept models. These models allow each group in your data to have its own baseline level, while keeping the slope effects the same across groups. This is perfect for data where observations are clustered, like students within schools. The intermediate level introduces random slopes, where the effect of predictors can vary across groups, and multiple grouping factors for complex nested or cross-classified data structures. This captures much more realistic variation in real-world data. At the advanced level, we explore complex covariance structures that model sophisticated correlation patterns, and Bayesian approaches that incorporate prior knowledge and provide full uncertainty quantification. The Bayesian framework combines prior beliefs with data evidence to produce posterior distributions. Developing practical skills is crucial for successful application of mixed models. This includes mastering statistical software, understanding model diagnostics, validation techniques, and most importantly, correctly interpreting and communicating results. Model diagnostics are essential for validating your mixed model assumptions. These 4 key diagnostic plots help you assess linearity, normality, homoscedasticity, and identify influential observations that might affect your results. Understanding software output is crucial for proper interpretation. Focus on fixed effects for your main research questions, random effects for understanding group-level variation, model fit statistics for comparison, and interaction plots for visualizing complex relationships. Mastering linear mixed models requires both theoretical understanding and practical experience. Start simple with random intercepts, progress through increasingly complex models, and always emphasize proper diagnostics and interpretation. This structured approach will build your confidence and competence in mixed modeling.